Hey everyone, welcome back to our series on math behind machine learning. I'm Kathan, and today we are diving into something that might seem simple at first glance, but is actually one of the most fundamental operations in linear algebra, machine learning, and computer science, which is the dot product. Now, you might have seen this formula that the dot product between two vectors is given by a dot b, which is equal to a1 b1 plus a2 b2, so on and so forth. But today we are going to go a little bit beyond that. We are going to see how to implement it in Python, and most importantly, why is it so crucial in machine learning. I'll show you some interesting applications. And if you're interested in just that, please feel free to skip to that portion. Now, what is a dot product? At its core, it's a way to multiply two vectors. I guess they've already given an example here. So two vectors are there, 1, 2, 3, and 4, 5, 6. Now the dot product is simply element-wise multiplication here, right? So 1 into 4, 2 into 5, and 3 into 6. But what is this number? What is this number 32? Right? So the dot product at the core gives us a measure of how similar two vectors are in terms of their direction and magnitude. So let's just take an example here. Okay, let me just open Excalidraw here. Now, if two vectors point in exactly same direction, so consider these two vectors. If they are pointing in exactly same direction, the dot product will be positive. The dot product will be positive here, and it will be maximized. Right? If they're perpendicular like this at 90 degree, the dot product will be 0. Right? If they point in the opposite direction, then the dot product will be negative. Right? So mathematically, I guess you've already seen that formula, which is like a into b cos theta. I guess you might have seen this formula. So here this a and b are magnitude of the vectors, and this cos, like this theta, is angle, right? So here in this case the angle is 90 degree, here the angle is 0, here the angle is 180, right? So in that regard, if you remember how cos theta works, if they are in same direction, cos 0 is 0. In this case, cos 90 is cos 0 is 1, cos 90 is 0, and cos 180 is minus 1. Hence it explains why this is positive, why this is 0, and why this is negative. Right? And what is this magnitude? This is simply under root and sum of squares of the each of the components of the vectors. Right? So that's the formula. So let's just quickly implement it. Then let me just open deepml again. Okay. So how are you going to implement it? We are given two vectors. Now the simplest solution is simply, of course, we can just use np dot vec1 and vec2. So this will work. This works perfectly fine here, but let's just do some bare Python implementation, because then it will help you a little bit more, right? So in the end, we want one number, right? So we can just initialize the result here to 0. Then what I can do is I have to go through all the elements element wise. So in range, length of any one vector, because of course both of their length is same. If it is not same, then it is an issue. So if you want, we can have a check here, but I guess under the constraints of this problem, it will never happen. So we can maybe put a check like this, length of vec1, if it is not equal to length of vec2, then we can maybe raise a value error of some sort, right? So vectors should be of same length or something like that, but that's fine, right? So here we are going through each elements of vector one by one, and we can just add what vec1 of I into vec2 of I, simply element wise addition, like element wise multiplication. We're just adding to result, and we can just simply return result. So let me just run it and see if it works. The manual implementation actually follows the exact formula, right? So a1 b1 a2 b2 till a and bn. Now NumPy is more efficient, obviously, right? As you can see, it works. Now under the hood, of course, NumPy's dot function is very much efficient and speedy, because I guess if you are following this playlist, you already know why. Because it uses optimized C code, takes advantage of the single instruction multiple data instruction, and can actually utilize hardware specific optimization. For small vectors, it actually doesn't make much sense, but I'll show you an example here. If you see, so let's say this is a manual one that we have written here, and this thing is the np dot. Let's just benchmark it. So if you see here, if you have a big array here, for smaller array it doesn't really make sense, but if you have a bigger array, the NumPy version is actually okay, 69.5 times faster. Okay, so I didn't pre-compute this. This came right now only. But anyway, so it is pretty fast. That's what I'm trying to say. Now let's move on to the practical application. So why is dot product so important in machine learning? Let's just look some concrete applications. First is cosine similarity. Now what is cosine similarity? Like in recommendation systems or in NLP, we often want to measure how similar two items or documents are. Now this is a very common these days, right? If you are into this field of LLMs, computing similarity is a very important thing, and that's where cosine similarity comes into picture. And dot product is a fundamental operation here. So basically, what is cosine similarity here is dot product divided by what is this? This norm. So norm is simply nothing. It's just sum of squares of individual components and their square root. Okay, so it's a fancy name for a norm of a vector. Okay, so they call it, I guess, the Euclidean norm. Correct me if I'm wrong. So this is what cosine similarity is. It simply compares two documents or two texts, right? And then, of course, the good old linear regression, right? When we perform a prediction in a neural network, like one forward pass, what we have to do is we will multiply our features with the weights, right? So there is a dot product happening here, and then we add the bias terms, right? So in a way, this is calculating the prediction here. Now, one another thing, I guess, principal component analysis is a very ongoing example that we are taking here, but it is a good example here when we want to project data, like a feature projection, right? So in dimensionality reduction techniques like PCA, we project data onto principal components, like the main axis of our data, using the dot products, right? So that's how we do it. I guess we have seen this again and again in this playlist, so you might be knowing it. And the last but not least, I guess if you're not living under the cave, you might be knowing about transformers, right? So in these models as well, we have this concept of attention mechanism, and we want to calculate the attention score. Again, a dot product is involved. Like there is a dot product happening between the query and the key vector, right? So that's why again dot product is very important here. Now, one last thing before we wrap up, here's a challenge for you. Can you implement this dot product without this bare implementation, but using NumPy's optimized functions? So what I'm trying to say is try implementing a function that computes the dot product of two vectors without using NumPy's dot function, but still using NumPy's efficient array operations. Can you do it? If you can maybe pause the video and try it. Otherwise, here I go. So what I'm trying to say here is use NumPy's efficient functions, but don't use the dot function. So let me just call it NumPy dot without the dot function. Okay, very good name here. Vec2. Don't use np.dot, but can you still leverage NumPy's efficient operations? What you effectively want to do is you want to first perform element-wise multiplication. So if you know that vec1 is a NumPy array and vec2 is a NumPy array, you can just simply do like this. This will actually return a new ND array with element-wise multiplication. So like the output of this will be each element of this final vector, this new ND array will be the element-wise multiplication, right? And what you want to do is you can just sum it up using np.sum, right? And then you can return it. So this is still pretty efficient, right? This is still pretty efficient. And yeah, I mean, that's that about this video. And to summarize, the dot product is a fundamental operation that measures similarity between vectors. It is implemented as a sum of element-wise products or sum of element-wise multiplications. In Python, NumPy provides a highly optimized implementation. Dot products are everywhere in machine learning: similarity measures, neural networks, transformers, and many more. So in future videos, we will build on this concept to explore topics like matrix multiplication, which is essentially multiple dot products working together, and that's exactly what happens actually in a lot of these models as well. So if you found this short video helpful, please like and subscribe for more math behind machine learning. So please drop your questions in the comments, and next time let's see what other question we have in a bag. Anyway, thanks for watching. I'll see you in the next one.